everybody. Thank you for coming to our session on special functions in geometry. My name is Bill Wood. I'll be your master of ceremonies today. I'm really excited about the speakers we have, so I'm not going to waste any time talking about how great they are. I'll just let them show you. Our first speaker is Rob Poodiack, who I go way back with. We've done some work together, and he's going to tell you about interesting squigonometric, I should be able to say this word, squigonometric series.
You applaud now, but will that be the case in 20 minutes? We'll find out. So I appreciate it, and I appreciate all of you coming out so early on a Thursday morning. This is joint work that I did with Bill. Bill and I have worked on a book project for about 5 years. We met in person in 2017, and thanks to the pandemic, this is the first time we've met in person since then. So every 6.5 years, whether we need to or not. So the p trigonometric functions, or occasionally the squigonometric functions, they arise from attempts to parameterize the curves x to the p plus y to the p with absolute values equal to 1, in the same way that the ordinary trigonometric functions sine and cosine parameterize the unit circle x squared plus y squared equals 1. And you can see what these p circles, as we'll call them, look like for various p. P equals 2 is the typical unit circle of radius 1. And as p increases, the circles get more squarish in appearance, and therefore we get squircles. There are several ways to define trigonometric functions. The way that we're going to do it this morning is by way of a coupled initial value problem, a CIVP, where we have two functions we're trying to determine, x and y, where x prime of t is going to be equal to negative y of t to the p minus 1, y prime of t is equal to x of t to the p minus 1. I should probably start my timer so I know when to stop talking. And the initial conditions will be that x at 0 is equal to 1 and y is equal to 0. And these coupled initial value problems like this do have unique solutions, and they have solutions. And so x will denote as cosine p sub p, and y will denote as sine sub p. That'll be the unique pair of functions that solve this coupled initial value problem. And we can define other related functions in the usual manner. So for instance, we could define the p tangent as the ratio of the sine p sine to the p cosine. And if we solve that initial value problem, we do come up with a relationship on a given interval that cosine sub p to the p plus sine sub p to the p is equal to 1 for all t in some interval containing 0, the initial value point. And we're going to think of the interval as going from 0 to some number we'll call pi sub p over 2. If we were dealing with the ordinary trig functions, it would be up to pi over 2. So we'll just put a little sub p on pi. We'll talk a little bit more about it. And these will define the first quadrant points of the p circle. And to determine what pi sub p actually is, we first need to examine the inverses of these new functions. So we're going to let y equal sine sub p of t to start. Then dy dt will, first of all, it's equal to cosine to the p minus 1, but that's the same as 1 minus y to the p minus 1 over p. That's a separable differential equation, and since sine of 0 is equal to 0 for all p, we can solve, and we get this expression for the arc sine. T is equal to arc sine sub p of y. It'll be the integral from 0 to y of 1 over 1 minus u to the p minus 1 over p. You know, you spit a lot when you say p's. I should have picked a different letter. Where we assume for now that y is between 0 and 1. In a similar way, if we set x to be cosine sub p of t, since cosine of 0 is equal to 1 for all p, we can write that the arc cosine sub p of x is equal to very similar integral, but we'll integrate from x to 1, with again x being between 0 and 1 for the time being. And using similar techniques, we can get that the arc tangent is equal to the integral from 0 to x of 1 over 1 plus u to the p to the 2 over p. And in all of these cases, when you look at these, you may want to think to yourself, if p is 2, note that these all do reduce to the usual trigonometric or inverse trigonometric functions that we know and love. So now from the arc sine definition, we can define general versions of pi. And so pi sub p, we're going to formally define to be 2 times the integral from 0 to 1, 1 over 1 minus u to the p minus 1 over p. In other words, it's equal to 2 times the arc sine of 1, or 2 times the arc cosine of 0 for all p. And this will give us that sine of pi sub p over 2 is equal to 1, and its cosine is equal to 0. And we also note that because there are only 4 lines of symmetry on a generic p circle, we end up with, and it can be shown through this integral through substitution, that sine and cosine at pi sub p over 4 is equal to the p through of 1/2. Okay? And this is what the p's look like. Because we're going to be talking about series a little bit later, we are generally going to consider p as a positive integer, but it can be considered, pi sub p can be considered a continuous function of p for all p bigger than 1, and you get a graph like that. And some quick facts about these pi's. It can be shown that pi sub 2 is equal to our known pi. Pi sub p is between 2 and 4 for p bigger than or equal to 1. It can be shown that the limit as p goes to infinity of pi sub p is equal to exactly 4. The area of the unit p circle is pi sub p square units. However, unlike in the p equals 2 case, pi sub p does not give direct information on the circumference or the exact angle measure subtended. You get all that when p is equal to 2. And since this session has to do with so-called special functions, here's one. Okay, pi sub p is equal to 2 over p times the gamma function of 1 over p squared over the gamma function of 2 over p, where the gamma function is defined as the integral from 0 to infinity of t to the z minus 1 times e to the minus t dt. If you've never heard of this function, it tends to be the most often grabbed continuous extension of the factorial. In fact, the gamma function of x plus 1 is equal to x factorial. Okay. Well, now that we've defined our functions sine and cosine, the p sine and p cosine, as solutions to that coupled initial value problem, we can expand the domains of all of these squigonometric functions. Sine and cosine to the entire real line through symmetry, and tangent to the real line except for odd multiples of pi sub p over 2. And in fact, you get graphs that look a little bit like that. These are examples for when p is equal to 4. And so what you notice here is similar, right? If you look at the squircle, the 4 circle, it's a little more squarish looking than the typical unit circle, and so what we have is that the sine, cosine, and tangent are the sine and cosine are a little more squarish looking. They corner a little more sharply. Tangent doesn't look too different, except that you notice that it's stretched out a little bit in period, okay, because pi sub 4 is bigger than pi sub 2, okay? And in a similar way, we can expand the domains of the inverse sine and cosine. So now we can obtain Maclaurin series for the arc sine function by first using the binomial theorem to find a series for 1 minus u to the p to the 1 minus 1 over p, and then integrate term by term from 0 to x. And what we end up with is, since arc sine of 0 is 0, we end up with this thing, okay? X plus, we have a product of p minus 1, 2p minus 1, all the way up to np minus 1. All over n factorial times p to the n times np plus 1 times x to the np plus 1, right? A little more stretched out than perhaps we'd like, but there's a nice pattern involved with these, okay? And it can also be written in this form, invoking the gamma function. So we'll come back to this form in a little bit, but you see the gamma function of p minus 1 over p plus n over the gamma function at p minus 1 over p. And for p equals 1 to 6, this is what these look like. So a quick glance at p equals 2 shows that we get the usual series for arc sine there, and we get some different things. The nice thing is when you plug in p's, these all boil down to typical numbers. And similarly, we can start with the binomial series for 1 plus u to the p over negative 2 minus p, what we were integrating to get the arctangent. To get something a little bit similar, we have p plus 2's instead of p minus 1's up there, okay? Kind of going up to n minus 1 times p plus 2. Same denominator, and similarly, we can also write that arctangent series in terms of gamma functions, okay? And this is what these look like. And again, in the p equals 2 case, we have a really nice, elegant series that if you ever try to use it for approximation, you'll be there a while, all right? It's an unfortunate thing sometimes in math, really elegant things to prove not to be overly useful, but it is beautiful. But we get these for the first 6 values of p. No, I'm not helping you with your homework right now. Okay. Now these series all converge to their assigned functions when x is between 0 and 1. The series themselves are hypergeometric, about which we'll talk in just a few moments. And they do converge for, at least for p bigger than 2 on negative 1 to 1. But if p is not even, it doesn't converge to the desired function between negative 1 and 0, because we lose some of the symmetry. If we go back for a little bit, for instance, we look at the arctangent. If we look at the p equals 2 series and the p equals 4, you notice that all of the powers of x are odd here. So we end up with an odd function, which is what we'd like our arctangents to be. However, for the odd integers, what we end up with is a function is represented with no symmetry at all, because we have both odd and even things. So you have to make adjustments if you want to use a series to approximate for a negative. Okay. Now, of course, what we want to do is say, well, what we would really like the series for is the actual functions themselves, the sines, the cosines, and the tangents. And so what we're going to do here is we're going to use series reversion. And if you look at Bill, he looks a little bit stricken because he's afraid that I'm about to do this step by step. I'm not, okay? But the idea of series reversion is that we have a Maclaurin series. T equals a function of x is a1x plus a2x squared, etc. And then what we can do, and as long as f of 0 is 0, we can write the series for the inverse function in terms of the variable t. And the idea is that each of the capital A sub i's can be written in terms of the various small a i's, okay? And now, given the series for the inverse p sine and inverse p tangent, we might think similar patterns in order would show up in the series for the p sine and the p tangent. And you may notice that title up in the corner. And here's the issue. These series grow what I've been calling polynomial tumors. There's patterns, and then there's something, and we would be half right. And these things are what I'm talking about. So if we look here, there's some order as we go from term to term, right? We have a p minus 1, we have a factorial, we have powers of p plus 1 and p, and we have a pattern going. But then what happens is we get these polynomial tumors. And I can tell you, I have no idea of the pattern of those. And the weird part is different people have done different versions of generalized trigonometric functions like these. And these tumors, when they go to derive their series, appear to be endemic to the topic. They just keep popping up. and different people get different polynomial tumors, but they do pop up. So a really good undergraduate project might be see if anybody can figure out what the pattern is. I mean, the only pattern that I've ever been able to figure out is, well, the power grows by 3 with each term. You know, so I know whatever the next one is, it's going to start with a p to the 11th term. That's all I know on that, okay? And so we end up with a series that the first 6 series look something like this, okay? And you can see the difference, right, going forward, especially as the terms go on, we get really wild fractions for these. Tangent and cosine end up not being immune from these polynomial tumors either. There is some order in what these Maclaurin coefficients are, but these tumors, again, pop up, and they're just really outrageous. So if somebody could figure that out before my talk ends in the next 6 minutes, I'd be happy. All right. And this is what the tangents look like. The tangents might be interesting only because, of course, typical for the usual tangent, Bernoulli numbers come into it. I have no idea how they play into those polynomials at all. And so those show up. Okay. And cosines look something like that for the first 6. All right. A quick word about convergence. While the customary and usual Maclaurin series for sine of t and cosine of t converge for all values of t, and for tangent of t it converges between negative pi over 2 and pi over 2, the same is not quite true for p bigger than 2. So again, here for p equal to 4, on the left we have the graph of sine 4 of t, and it may be a little bit hard to see on here, but the red dash is I believe it's the degree 45 Maclaurin polynomial. And on the right we have tangent 4. And so for the Maclaurin series for the tangent converges between negative pi sub 4 over 2 and pi sub 4 over 2, while the series for sine 4 of t converges on an interval that we'll just call negative epsilon 4 to epsilon 4 for now. And the hyperbolic versions of the p sine and cosine turn out that they have vertical asymptotes at plus or minus epsilon p. And it can be shown that there is no smaller issue with these functions. So for the hyperbolics, you would solve a similar coupled initial value problem, but with the minus signs gone. So when p equals 1, we get that. P equals 2 is the typical cosh and sinh. But then, when we get to 5, there are vertical asymptotes. And the vertical asymptotes are getting tighter. They're there for p equals 10, but they're getting tighter and tighter. They seem to be heading toward plus or minus 1. And how about I hit the right button? There we go. And so it can be shown that epsilon p is, now keep in mind, right, if it's a vertical asymptote for the sinh, it would be the limit, it would be a horizontal asymptote for the inverse function. And so we can show that we end up with this integral. So we get a ratio of gamma functions, but if you graph these out, for 2 you get infinity, which makes sense, and right, we just press on toward 1 as we go. And you can show that it goes to exactly 1 in the limit. And the other relationship to look at is that if we have a number omega that's a pth root of negative 1, then cosine sub p of omega t is equal to the cosh sub p of t, and sine sub p of omega t is equal to omega times sinh sub p of t for all t between plus and minus epsilon sub p. And so therefore, the Maclaurin series for sine sub p of t and cosine sub p of t have radius of convergence epsilon sub p. And again, so when p is 2, we get that the series converge for all values, but it actually has a finite radius of convergence that squeezes down toward 1. Okay. The other issue we have is for the sine and cosine and tangent is that odd integer problem. So for instance, here is a graph of sine sub 3 of t, And the Maclaurin series converges nicely up until we get to pi sub 3 over 2. But then as we go backwards, it goes kind of off the rails as we head to the left. Part of that has to do with the fact that we're imposing symmetry on it. Okay? And notice that epsilon sub 3 is pi sub 3 over 2. Coincidence? Absolutely, as it turns out. Okay? All right, yeah. And I mention it because if we go back to, and I'm getting the signal that I have about a minute here, if we look at epsilon sub 4 here, that number turns out to be something called L over 2, or L is what's called a lemniscate constant. Okay, and again, that just seems to be a coincidence in this case. All right, I prepared way too much material, but you folks have watched the end of movies on TV when they show them, right? So here's kind of the credits. You're used to reading this, right? But if you're really interested in that, you can go ahead and scan that QR code if you want to get the slides at any point, okay? I thank you for your time and attention this morning, and I'm happy to entertain any questions you might have. Thank you. Yeah.
Is there a complex analog of this, like complex exponentiation with these?
There is. In fact, there's a generalization. If you follow all of this, there's a generalization of the exponential function that comes from this, where you can define a generalized exponential to be just, so the p exponential would be the sum of the p cosh plus the p sinh, which means that essentially when p equals 2, you have the usual exponential function, which goes from negative infinity to infinity. In a way, what happens is as p grows, you're taking the lifetime of the exponential and compressing it into finite time. So the generalized exponential will actually hit 0 at negative epsilon sub p, and will have a vertical asymptote at positive epsilon sub p. And in fact, it does have an inverse of a generalized logarithm. Yeah?
Have you looked at for which p pi sub p is transcendental?
I have not, but I do know, I believe, because of its relation to the gamma function, it's been proven that gamma of 1/3 and gamma of 1/4 are both transcendental, and so therefore pi sub 3 and pi sub 4 are transcendental as well. That's all I got on that.
Go back to the gamma function.
Yeah, I mean, clearly on the other hand, if p is less than 1, you can get rational, you can get rational values of pi out of that. It's continuous. So yeah, so there's lots of values. But for instance, pi sub a half is 2/3.
Okay, our next speaker is Joe Fields. We'll be talking about Fourier analysis with squiggles.
Hi, everybody. Thank you. So that's my abstract. I'm going to do some numerical analysis to figure out some of the Fourier coefficients for p-circles. The basic layout of my talk is like this. There's going to be 3 pieces. There's just some initial material I wanted to get through, and then I'll talk about the numerics approach that I took to determine these coefficients, and finally just in a menagerie of results. So let me roll with it. Just in case people hadn't seen Rob's talk, and a few people did squeak in between the talks, I thought I'd quickly say, what's the basic idea of squigonometry? That's the p equals 4 squircle. It's halfway between a square and a circle, so squircle. The equation looks like a power x to the p, y plus y to the p is 1. There's absolute values in there for the cases where you're looking at odd values of p because they'll mess it up. But if you basically just keep track of the x and y coordinates as you move around those various curves, you get an alternative to trigonometry. You get squine and cosquine functions. And in fact, you get an infinite number of trigonometries. So I thought I'd try to do a little animating to show this. These are the p-circles starting at p equals 2 and then heading towards plus infinity. And as you can see, it ends up looking like a square at infinity. Actually, it only went to 50, but close enough. And then heading back down towards, these are the p-circles for things less than 1. At close to 0, you get that little plus sign thing. So. All right, so a couple of disclaimers. First, this is not really a math talk. I'm mostly here to show you some pretty pictures. And, there'll be no theorems. There's actually no proofs for sure. And I'm really not qualified to do this. Honestly, I'm a coding theorist, so this is not my field. But on the other hand, yeah, you're going to understand every single thing, I promise. You know, it's going to be good. You may be amused. I don't know. I've been recently accused of having dad joke humor, so maybe you won't be amused anyway. But there will be good pictures anyway. All right. So and also some acknowledgments. Squigonometry as a subject was introduced to me by our previous speaker, Rob Poodiack, so I owe him a debt here. And I just finished reading this book by Poodiack and Wood, Squigonometry, the Study of Imperfect Circles. It's literally a goldmine of cool undergrad projects. So if you're looking for an undergraduate research project, I strongly recommend downloading a copy of that or getting yourself maybe you can get a signed copy from the authors. Another person I owe a great debt to is Grant Sanderson of the 3 Blue, 1 Brown YouTube channel. The guy's a rock star, and just I've learned so much from him, including he's released the software that he uses to produce all these cool mathematical animations on 3B, 1B, and I owe him something for that, although the version of it I use is what they call the community edition, which is run by a really intense group of developers. Benjamin Hockel, that I mentioned here, has written or has composed a bunch of tutorials on how to use this software, and it's good stuff. Anyway, so a little bit of personal history, not real history, but the reason I got interested in Fourier series having to do with squig functions, because I had a former life before I came over to the dark side, which was in mechanical engineering. And in mechanical engineering, there's this kind of common problem of generating motion profiles using cams. And the cam that I was looking at, we couldn't really describe well. We had what we termed a fractal differential equation to describe the shape, but it didn't have an easy definition. And so I started looking at the Fourier series approach for this thing. It had to be periodic, right? It had to have a Fourier expansion, but I couldn't figure out what it was. And then in around 2010, I may be plus or minus epsilon is like 4 for that number. I saw this presentation by Rob about squigonometry, and I wondered if that was what was the problem, that the sine and the cosine didn't make a solid basis for the space of periodic functions in terms of the one I was interested in. It just wasn't in the area where the series converged. So might that create a more natural basis for doing Fourier analysis? I'm going to show you just pictorially why this might make some sense. This is roughly the curve I was interested in. It's called a transfer dwell, return dwell cam. So it's got 4 phases of motion. Transfer is where you go from like -1 to +1 here. That little looks like a sinusoid. Dwell is staying in place, and return is coming back along a sinusoid. And then the second dwell is also staying in place. They're clearly periodic, but didn't seem to have good Fourier numbers. And then that's a crude example of what the squine and cosquine looks like for p equals 4, although it's not parameterized correctly, so you may notice there's a little glitch in the picture. And anyway, it seems like it's got some of the characteristics of that transfer return dwell thing, that it's got kind of flat spots on it. So I don't know. I thought it might get somewhere. And at a certain level, this should be just linear algebra, right? We're just trading one basis for another, but it didn't ever work. And finally, I just gave up, honestly. I couldn't get it to happen. And then last year, I came across this 3 Blue, 1 Brown series. It's actually a nice like 4 or 5 part series on the heat equation and how Fourier originally came up with the ideas behind Fourier analysis. And I'm going to show you just a few seconds. Not on the YouTube, I'm not. I forgot that I had that one slide in there that needs video. But I'll just visually describe, or try to audibly describe what he did. They'll have a whole vector sum of tiny little arrows, each one rotating at a fixed rate and at different fixed rates because they're the components of a Fourier expansion. And those arrows headed tail to head come out to a little point which draws whatever the heck he wanted it to draw. He's got things like, there's a part in that video where he literally draws a portrait of Joseph Fourier. It's mind-boggling what you can do by combining complex exponentials. So I thought if he can draw things like, a portrait of the man, I can certainly draw a squircle that way. And so I decided that I would. This required a bit of a change of perspective. My understanding of Fourier analysis honestly came from an undergrad course in differential equations that was an embarrassing number of decades ago. And it was just the 1D version of things. How do you take a periodic function and decompose it into sines and cosines? And I mean a function of one variable, right? This variant of things that Sanderson was doing on his 3 blue, 1 brown video was two-dimensional. He's thinking about a periodic function as a mapping from S1 to C, and then using a sum of multiples of things that look like a complex coefficient times a little complex exponential. That's the little spinning arrow. The complex coefficient basically gives you an initial length and an initial phase angle, might call it, and then the thing begins spinning and you add them all up and you get cool pictures. And then, of course, if you want to get the sort of old school version of Fourier analysis that I grew up on, you just pull out the real and imaginary parts with Euler's formula. So it's more general and it gives you the same stuff. So that's Fourier analysis as I originally knew it. You have got a separate transform for the cosine and the sine, and they're both integral, where you integrate the function against a kernel, but it's trigonometric kernels. And this is the sort of more modern thing where you're integrating against a complex exponential kernel. And, I didn't mean to zoom, what did I just do? Sorry. The differences are notable, though. I think I go to that in the next slide. That's the inverse transform. So making this switch has some pros and cons. One, it's simpler. You've just got a single function, or a single transform, and it's inverse. But there's a nice connection between the function, the direct transform and its inverse transform. But then there's some weirdness that you have to deal with. There's negative time. You saw the integrals go to minus infinity. And there's negative frequencies, which I took a little while to think about what that means. And then, doubly infinite integrals. So there's a nice reduction that happens, though. The things I'm interested in are simple closed curves, and despite the fact that there's all these different pi's to deal with, as we saw in Rob's presentation, I can make it so that I parameterize them over 0, 1. And then the form for the complex Fourier coefficients is just that. Okay, I suppose it's a little complicated, but it's not very hard. It's a complex path integral, and it goes from parameter t 0 to t is 1. I can beat that to death. I can get you numbers for that sucker, right? So before I go off to that death beating I mentioned, I want to just say a quick thing about the negative frequencies, because this was kind of cool, and I liked it anyway. Negative frequencies just mean instead of a little arrow that's rotating in, say, the counterclockwise direction, I've got a little arrow that's rotating at that same rate in the clockwise direction. And you could combine these, and I just thought it would be fun to show you what you get if you take two little arrows with their own phase angle and lengths and begin counter-rotating them and see what the sum looks like. Maybe somebody would like to take a guess at what you get, but I'm going to show you, I hope I'm going to show you a video. So that's just a couple of random complex numbers. There they are as arrow versions. That's their sum. What is that yellow arrow doing while these guys go spinning around their little spinny world? Maybe you can guess. Well, here, I'll go ahead and show you. Yeah, it traces out an ellipse. So one could do a version of this whole animations that I'm going to be doing where you had elliptical epicycles instead of circular epicycles. Okay, so let's get into the nuts and bolts. As a starting point, you need to have a decent parameterization of the curves you're interested in working with. And occasionally for this part, I've had to jump to piecewise functions, but not always. Then you need another function that tells you sort of what's the goal of your parameterization. For instance, if you want arc length, then you need to have something that gives the speed of motion as you move around your curve with respect to this original parameterization. And then what I basically do is use Newton's method to dissect the curve up into a bunch of little chunks. I didn't start my timers, Bill, so you're going to have to let me know. Basically, there's one little issue that can come up when using Newton's method. It goes chaotic occasionally, so you have to make sure your parameterization is good enough that that doesn't happen. And then what I did for each chunk, make a cubic spline, and that gives me something that's totally computational. I can work at points all the way around the squircle or whatever curve I'm after using the splines. And because I make a lot of chunks and make the splines agree in both position and derivatives, you know, it's almost exactly, like down to 10 to the minus 12th values of the original pieces. And then finally, I don't actually integrate, although it could with splines. I just use a Riemann sum to approximate the integral. So parameterizations. Well, you know, like we just saw there's a lot of different values of pi when you're doing squigonometry. And it's not just about that there's all these different p circles. There's also the issue of how do you travel around them? If you travel around them, you know, with constant arc length, at constant speed, let's say, you get one parameterization. If you care about how area is swept out, you get another. Something that's kind of cool is that at p equals 2, all these different notions of traveling around become 1. It's bizarre, but radian measure is really special in sort of mysterious ways. So I have concentrated on the two kinds of things I just mentioned, traveling by constant arc length and by constant swept area. Okay, so we're ready to show you some stuff. Okay, not quite. I got to jabber a little more. Basically, the process was I use a kind of a two-phase thing. I used Sage to compute the Fourier coefficients, and then the MAA software from 3 Blue 1 Brown to make animations. And I never did actually get to what I'd hoped to do was to show you a way to sort of compare the Fourier coefficients of one parameterization of a squircle to another. Never happened with time and energy or finite resources. So I thought it would be fun once I had some of these things to just check it out for an ellipse, because think about it, the arc length parameterization and the swept area parameterization for an ellipse, they're physically interesting. And yeah, so here's arc length. It's not exciting. And this is my version of trying to use 3 Blue 1 Brown's thing directly. I never got arrows to work right. But there's a constant arrow, meaning there's sort of a constant term of a frequency 0 term, and then there's something that dominates that is sort of a circular motion, and then finally there's some little stuff off the edge. We'll zoom in and watch as we move around. But really, there should be at least 5 little arrows, and I think that we're really only seeing 3 of them, and it had to do with the software automatically rescaling things. So I basically had to ditch that software, that version of the software anyway, and switch to something where I just used little line segments. Now, I hope you can just imagine the arrowheads on these little line segments. This is the same picture, but just without the arrowheads. And I was able to now, you know, dictate what the stroke width of these little line segments was. So I get you can see a little bit more of the small components, the higher frequency components of the transform. And when we get in zoomed fairly tight, you'll notice some really tiny little stubs of line segments that are in there. That's, in this case, it's frequency 5 and 6 showing up. All right. I've got to show you swept area for the ellipse just because it's really cool. I'm going to probably have to truncate some of this because of time restrictions, but the way this thing unwinds is really awesome. And then there's this sort of whip-like effect as the planet goes closest to the sun, where it's really speeding up. And then at the apogee, I think it's called, where you're far from the focus, it has to slow down, and you watch the coefficients all kind of fold up together. I find it mesmerizing to see what this looks like in practice. And for this parameterization of the ellipse, I had to have a whole lot more Fourier coefficients to get a reasonable, a close fit to the curve. And the thing is, you're not just fitting the curve, you're fitting a parameterization of the curve. It's not just the physical thing, it's how you move around that thing that matters. There's an alternative view of this, which maybe I'll just show you the swept area one is to do a little animation of what does it look like as you increase the accuracy of the Fourier approximation. So at frequency 0 alone, all you get is a point, and then as you add, actually the point's in the wrong position, but this is it slowly adding more and more terms to the Fourier series, or higher and higher frequencies added. And I think in this case, by the time I got to frequency 12, I was done. I was more or less on the curve, like within 1 part in 1,000. So then the thing we're actually all interested in is what do you do with a squircle? The obvious parameterization would be this one to start with, I think, but it's really bad. And just, it breaks the speed of light anywhere near -1 and +1, which we all know isn't good. And yeah, so I found this kind of cute hack, which was just to get things, started. You can basically think about taking the regular circles parameterization and then scaling it radially so that you get something that lies on the x to the 4th, y to the 4th equals 1 curve. And that dividing by a 4th root of something is the thing to do. So starting with that parameterization, I was able to put it through this machine that I built and get our various, how much time do I have now? A couple of minutes for the actual movie? 2? Okay. I think these are each about 30 seconds. So it's honestly, I think, not that interesting, right? The, you end up with it's dominated by the frequency 1 term. There's a big rotating arc, and it's got this little tendrily whip-looking thing on the end that takes care of keeping the point on the actual squircle. And in this case, you're pretty much on the squircle, like, again, to within 1 part in 1,000 by the time you get to like 5 terms. So that actually says something, I think, that's a little interesting mathematically. These Fourier series for squircles converge rapidly. You don't need a whole lot of the high frequency terms to get an understanding of it. I had the I don't know what to call it, a hypersquircle, where it's p is equal to 6, but I decided to forego that one in favor of what it looks like when p is infinity. Why not jump from 4 to infinity? And it looks more or less the same, but it's still a pretty cool picture, and well, I'll let you judge for yourself. Basically, it still is dominated by the frequency 1 part, and then it's got a more interesting whip thing on the end that spins around, that keeps you on the square as that big guy moves. And if we watch it as we zoom in, and you can get a better view of what that whip on the end does, it's pretty cool. There is a what do they call it? The Gibbs phenomena is rearing its head in here. You see how the point begins kind of wiggling, and as you get to the perimeter or the corners of the square. The last frame here fills in what the actual, I think that's degree 12 Fourier coefficients look like, what the approximation looks like, and you can see it gets a little wiggly near the corners, but I'm sure a few more terms would get it. Well, thank you, everybody. Actually, that is the end of my talk. I didn't do the thing Prob did, but thanks for your attention, and I'd be happy to take any questions.
Thank you, everyone. I want to start off by thanking the organizer for the invitation. It's been a pleasure to be here. So I'm here to present some joint work with my colleague and co-author Pishing Ding from Illinois State University. So we explored some complex analysis over these unit P circles. So here are some references, and this is also just to give you some context, some of the genesis of this research. A few years ago, I was asked to teach an introduction to undergraduate research course at my university, and then I found this project-based guide to undergraduate research. It's a beautiful book, Springer publication, and I was shortlisting some topics, and I picked 2 topics, and one of them is this paper in that book by William Wood and Robert Poodiack, and the second one was something in graph theory. And it's kind of interesting how history could have gone differently. If I had taken this other project, I wouldn't be here to give this talk. So we worked on that, and my students and I, we wrote our first paper, published in Mathematics Exchange 2021. And shortly after that, my colleague Pishing got interested in this, and we said, okay, let's explore what's happening over the complex plane. And that is what I'm going to show you today. So some of this is going to be a recap, because you have seen this already a couple times this morning. So let's start with the unit circle. So the classical trigonometric functions sine and cosine are well known to parameterize this curve, x squared plus y squared equals 1. Now, what is t? Well, this is very important. We should understand what t is. What does t represent here? T represents one of 2 things. Either the arc length, let's see if I can show this here. So this arc, or twice the area of the circular sector. So either it could be the arc length parameterization or the areal parameterization scaled by half. So any one of these 2 things. And this is very important to keep in the back of your mind as we go. All right. What about unit n circles? Okay, so it's p circles, but in the second paper, we decided to switch to n circles. So for any integer n greater than or equal to 2, you can consider the curve x to the power of n plus y to the power of n equals 1. And note, there is no absolute value here in this version. It is just x to the n plus y to the n equals 1. Now, here are a few graphs which I got from Desmos. And for even values, there is a beautiful symmetry, bounded curves, but for odd values, so these are unbounded curves, right? So these are curves. Now, the big question here is, can we parameterize these unit P circles to generalize the ordinary trigonometric functions? And there is a lot of literature on this. And we have seen some talks and papers by Bill and his co-authors. And we explored this. Can we generalize, right? So to generalize, let's recall the ordinary definition of sine x. And you can define sine x in multiple ways. You can use power series, you can use differential equations, as we saw in the first talk, or we can use integrals. And I'm going to take integral approach for reasons which will be clear in a few minutes. So here is one definition of sine x. Sine x is a function which is defined from the interval minus pi over 2 to pi over 2, going to minus 1 to plus 1, which is defined as the inverse of this invertible function. Y going to the integral 0 to 1, 0 to y of 1, the square root of 1 minus x squared dx. Now this function here, it's a nice function, it's continuous, it's differentiable, it's monotonic, blah, blah, blah. Therefore, it's invertible. So you can talk about its inverse, and that is your sine x. All right, and in this definition, once again, t is going to, sine t is the y-coordinate of a point on the unit circle where t signifies either the arc length or the, actually twice the area of the circular sector. Okay? And of course, this is the y-coordinate, and the x-coordinate will be the cosine of t. So what is the definition of sine sub n of t? Okay, we want to generalize this. Now, for n greater than 2, we're going to set up this notation. an is going to be minus infinity for odd values. And because, as I said, for odd values, these are unbounded curves, and for minus 1 for even value. And then I'm going to just mimic what I did earlier. Just when n is 2, you get that arc sine, right? So I'm going to define this function f sub n, which is going from a and 1 to the real line, which is going to be that integral. Again, it's differentiable, increasing, and therefore it's invertible, right? Now, inspired by the fact that arc sine 1 is pi over 2, and we have seen this in previous talks, we can define pi sub n such that the value at 1 of this function is pi n of 2. So in other words, pi n is twice the definite integral. Okay, at this point, I should mention that, like last year when we were celebrating the Pi Day on March 14th, I told them there's nothing special about March 14th. Every day of February, March, and April can be Pi days for generalized phi values. Okay, and then now just take the inverse of that function, and that is your sine n, sine sub n. So sine sub n is a function going from that interval to an comma 1, and once again, an is minus 1 for even values and negative infinity for odd values. And then you can define cosine t to be the nth root of 1 minus the nth power of sine n, and you get this generalized Pythagorean relationship. And this one is going to parameterize the right half plane of the curve Cn, all points of the form x comma y, where x to the n plus y to the n equals 1. It's only the right half because cosine is positive here. And as desired, under this parameterization, T will be twice the area of the sector. So OAP, O is the origin, A is 1, 0, and P is that moving point. Okay, so we achieved what we want. But note, it has nothing to do with the arc length parameterization. Only for P equals 2 or n equals 2, it's a coincidence that the arc length parameterization coincides with the areal parameterization, but for other values, it doesn't. Okay, so in particular, the area bounded by the curve Cn in the first quadrant is pi n over 4. And this is very important, and I'm going to come back to this at the very end of my talk. Yeah? So why is it pi n over 4? Well, at 1, it's going to reach pi n over 2, or pi over 2, right, for p n equals 2, right? But it's supposed to be half that value, so it's pi n over 4. So the amount of area you pick in the first quadrant is going to be pi n over 4. Okay, so now towards complexification of these functions. So whenever you want to complexify, you can just see what happens in the classical story for n equals 2, the ordinary trigonometric functions, and try to mimic that. So you can take the power series approach, and we know that from calculus that sine x has this Maclaurin series, which is defined for all values of x. This power series has infinite radius of convergence. Okay, and if it has infinite radius of convergence, the general theory of complex analysis tells that you can feed any complex number and you get a reasonable answer, right? So then you can define sine z to be that function. So this one is a theorem, and that is a definition. Okay, so there is nothing wrong with that. Problem solved, right? So now the question is, why don't we do the same thing for generalized sine functions? Well, let's do that. And I think we have seen this earlier today. You can take the definition, fn, which was kind of the inverse function for generalized sine n function, and the integrand you can expand using Newton's binomial series. It's an absolutely convergent series. You can do term by term integration, all the general theory. And then you can get a power series, which is going to have a non-zero derivative at 0. Therefore, the inverse is also going to be an analytic function. Namely, it admits a power series. And repeated differentiation, and this is where that polynomial tumors, or what you call them, they start emerging. You take this identity, a sine n fn of y equals y, by definition, and then repeated differentiation is going to spit out the successive derivatives of the generalized trig function at the origin. And there's a more systematic way to do this, that is Lagrange inversion formula. And this is what my students did in the undergraduate research course, where we started seeing some patterns having to do with the Stirling numbers of the first kind or second kind. It's in the paper. All right, so then you get some formulas of this form. And now note that these are now definitions. I'm going to define sine 3z for any complex number z within the radius of convergence to be that. And you can do that for all values, right? But for me, this is not very insightful. First of all, I don't see a clear pattern, although there see some partial patterns coming from Stirling numbers. I still don't see the full story. And also, the radius of convergence is hard to compute here. So what we're going to do is going to take a geometric approach, complex geometric approach. So we're going to identify sine n's natural domain of analyticity in the complex plane and describe it as a conformal equivalence between two domains which are simply connected. Okay? Now, the fact that there is a conformal equivalence between these two domains is not a surprise. That comes from the Riemann mapping theorem. But in our research, we were actually able to construct explicitly that mapping. And as a bonus, we got some real applications. When I say real, there's some pun intended there, and you will see that hopefully in the last end of my talk. Okay, so some notation. I is going to be the interval 0 to 1. J is going to be the interval 1 to infinity. And for any subset of the complex plane, A times S is going to be the set of all points of the form A times Z, where Z varies in S. Omega n is going to be e to the I 2 pi over n, that's specific nth root of unity. And an is the value where fn takes the value 1. So that's like generalization of pi over 2. Sine pi over 2 is 1, right? Sine n pi n over 2 is 1, right? An, that's an. And bn is the rotation of that complex number by that root of unity. And last but not least, we're going to have this shape Vn. It's an open wedge of the complex plane consisting of all points in polar coordinates with positive radius and the angle between 0 to 2 pi over n. So when n equals 4, that is just your first quadrant. Okay, let's begin. So let's start with n equals 4. As I said, the omega 4 is just I, complex number, and V4 is the open first quadrant. We want to analytically extend this function -1 to 1 to R, so that will be sine inverse, right? Or sine 4 inverse, right? So you want to analytically extend this one. Now take any point in V4, the first quadrant, and I'm going to define this function 1 over 1 minus z to the 4th whole to the 3/4. And then here, I'm going to require that at 0 you should pick 1, the principal branch of the power function. And then it's a simply connected domain. So therefore, there is a path-independent primitive defined to be f4 of z going from integral 0 to z, k4 of zeta d zeta, right? So that is a path-independent integral. Now let's talk about continuation. So between 0 to 1, what's happening? Well, that is the real case where k4 is not defined, all right? So there is a pole at 1, but however, f4 of 1 is defined. So that integral converges, right? So you get a finite answer there. And then, so the interval 0 to 1 maps to 0 to O to A4, okay? Now what happens when you go past that singularity? 1 to infinity. So that's where the surprise is. For x greater than 1, when you try to analytically extend it past 1, so the input is a real number, but the output is a complex number, because there is a branch of the power function, and for continuity, you have to introduce that phase factor e to the I3 pi over 4. So, which means the output values go up in that direction. So in the direction of A4 to P4. So f4 of x is f4 of 1 plus the integral from 1 to x of k4t dt. And you work it out, and what you end up showing is that the function f4 maps the interval j from 1 to infinity to that little green part there, from A4 to P4. And then you similarly do this over the imaginary axis. What's happening from 0 to I? That will be mapped to 0 to B4, which is the rotation of this complex number by 90 degrees. And then for values past I, in the vertical direction, it just moves this way from B4 to P4. Okay? So you got on the boundary what's happening on the interior. So the argument principle can be used to show that F4 maps V4, this region, bijectively onto into the interior of pi 4, which is that isosceles right triangle there. And then we can, once you get the F4, you can invert it. It's bijective. So sine 4 is now defined from that right triangle pi 4 to V4. And then you can use Schwartz reflection principle to just map it all the way around. So at the end of the day, you get sine 4, which is mapping from this, this is called, I call omega 4 to this complex plane. All right, so what are some properties of this function? So I'm going to let sigma 4 denote the complex plane minus this 4 rays removed. And then sine 4 is a conformal equivalence. It's a biject analytic map from the interior of that domain omega 4 to sigma 4. So that's a picture here I have, okay? And these points, P4 and all the rotations of that, those tend to be the poles. You get the sine function goes to infinity when you pick a point z that's approaching one of these P4 and then all the 4 rotations of that. And the continuous extension maps the boundary minus these points 2 to 1 onto this union of these rays. Okay, those are some properties, but I think the big takeaway message here is that you have this conformal equivalence from one domain to another domain. Both domains here are simply connected. So in this case, you have this square, and in this case, you have this complex plane minus 4 rays removed. And this is where I can speed up a little bit. You can just generalize this for arbitrary values of n, keeping in mind that this time, after you go past 1, you have to rotate by an angle of pi n over n, and here, as you go in this direction past the rotation of 1, you have to go with an angle of pi n over n. So when n equals 4, so you get a convex polygon, but for values of n bigger than 4, you get non-convex polygons. So these are the natural domains of analyticity for the generalized trigonometric functions. So here are the domains, and those are the ranges of your function. So for sine 3, you have to remove 3 lines. For sine 4, you have to remove 4 lines, etc., etc. So we were very satisfied when we found this because these are beautiful geometric shapes which we didn't know before. And I'll just put the main theorem here. There is no difference between this one and the sine 4 except that I generalized everything for n, okay? So I guess I can just fast forward that in the interest of time. But the radius of convergence of sine n, now it's pretty obvious. What's the radius of convergence? So what is the largest positive real number Rn shows that sine n is analytic? Well, the obstruction, the bad points of the P4. So what's the biggest circle you can draw staying away from these bad points? Well, simple trigonometry tells you the radius of convergence is pi n over 4 secant pi over n, okay? Okay, so finally I should end with this one. I put this on this MAA app just to intrigue people last night. So I promised some real applications, and here is one. So you can give it to I don't know, this could be a Putnam problem or a calculus problem. So you take the Fermat curve x cubed plus y cubed equals 1, and show that the region bounded by that curve and its oblique asymptote is trisected by the coordinate axes. Okay, so there are 3 regions, one in blue, one in red and green. We want to show that all 3 have the same area. Well, you can just use brute force integration to get this. But with all our techniques, we prove this effortlessly. Well, it's pretty clear that the blue and the green have the same area by symmetry. And it's enough to show that the red and the green have the same area. And I told you what is the area of the red in the first quadrant. That is pi 3 over 4. So I'll be done if I can show that this area is pi 3 over 4. Well, so for that, you need to understand that this area is the areal parameterization, well, scaled by half, right? So what is the first negative number? Alpha shows that sine 3 alpha is negative infinity. Because as you go down, all the way down at negative infinity, well, what is sine x? It's just the y coordinate of that point, right? At negative infinity, right? So what is that value? Well, a glance at the domain of the sine 3 tells that the value is equal to omega 3 p3. So therefore, what is the area? Well, it's half the areal parameterization. You have to scale it by half. So you do half times the value of the absolute value of alpha. Well, omega is the root of unity, so it's just the distance from 0 to p3, which is the same thing as the distance from 0 to a3, which is just pi 3 over 4. So Thank you for your attention. And so if you want to know more, you can scan that QR code, which will take you directly to the paper on which this talk is based.
Please welcome Pat McDonald of New College.
Thanks very much for the invitation, for the very kind introduction. It has been a long time, you know. I think back then I had much more hair, way more hair. Okay, so I think I should start with a little kind of outline of what I've got planned. Let's see if I can make this work. There we go. First, this is all joint work with Jeff Langford. Here's the outline. The first thing I want to do is a computation that everyone in the room I hope understands, right? And it will give you an idea of the machinery that I'm going to use later on to prove much more sophisticated things. But nonetheless, it's entertaining. All right. Then I'm going to mention some facts about Brownian motion and exit time. Following that, I'm going to talk about geometric invariants. And these invariants are best understood using probability theory. Okay. And then I'm going to write down some curious sums, right? It turns out that some of them have appeared in print before in the work of Ramanujan and others. They have a long history. I'll say a few words about that. Right. Mostly, what I really want to do is just to convince you that there's a lot of interesting work to be done. This is kind of the tip of the iceberg. I can give you some ideas how things extend at the end of the talk if you're interested. Okay, so let's begin. Suppose I take a function just on the closed unit interval, say a polynomial. It vanishes at the endpoints. That's important. Okay. And then I look at standard Fourier modes on this interval. Right, so phi k is just a sine function. I can go ahead and represent u on this interval, right? It's a sum of coefficients times these Fourier functions, yeah? And I can tell you what the coefficients are. You get them just by integrating. And I think probably everyone in here could do this integral with sufficient diligence. Here's what you get, yeah? Right, well, I can do other integrals. Here's an even easier one, yeah? And once I do these two integrals, now I get an expression for the function I started with, kind of an explicit expression that I can integrate. Okay? So all I did was piece together those two calculations. That's it. Right? And what you see here is that something that looks like Riemann zeta function at 4 appears on the right-hand side. Right? And u1 here is a polynomial. I can explicitly integrate that. So I do a little bit of work and I get this. Here I'm summing over the odds, but that's not really a problem because I can always write the odds as a difference between everything and the evens, and then it's very easy to pull out a factor in that second term. Okay? So in the end, I get this expression. All I did was arithmetic. All right, and so this is a well-known fact. You can find it on the Wikipedia page if you look up special values of the Riemann zeta function. Okay. Now, it turns out that I can actually iterate this calculation. Right? Here's what I do. I think about where those sine modes are coming from. They're coming from a solution of the Dirichlet problem, right, on the interval. And by that, I just mean two derivatives of u, right, and equals some function, and u on the boundary is 0. So I'm going to choose the right-hand side to involve the function u1, and I'm going to give you some idea for why that is in the not-too-distant future. But suppose I go ahead and I write down this boundary value problem on the unit interval. Well, look, the right-hand side is a polynomial. I can integrate that if I want to, so I know I can solve this problem, right? But what I'm really interested in is just integrating u2. So I don't actually need to solve that problem to integrate u2. I can just integrate by parts the things I've already seen. If you don't believe it, you should do it. It's an exercise. It'll keep you out of trouble for a while, okay? So I go ahead and integrate, and what I get is an expression that looks like this, and you will notice that once again I see something that looks like a zeta function, special value, on the right-hand side, and so I can do all the same tricks. I get a formula for zeta of 6, and you can check, as another exercise, if you're interested, yeah, that this is what Wikipedia says is the answer. Okay. All right. In fact, I can keep doing this. And what I get is an expression for zeta at the even integers. Okay? And all of this has been known for a very long time. Here's what I want you to take away from this calculation. The choice of U1 drives everything. Right? After that, it's, do you know something about the Dirichlet problem on an interval, and can you integrate by parts? And it turns out that that is a horrifyingly general fact, right? And that's what this talk is really about. Okay? So it goes back to figuring out why choose U1. Okay? What's the intuition behind the choice? And it turns out the intuition behind the choice is given via probability. So that's the next thing I want to talk about. I think I got to check time here. Yeah, okay, so I start with Brownian motion. I'm not going to actually tell you what it is, but it's helpful if you know it. You should think of things zigging and zagging, right? I'm going to let tau be the first time that Brownian motion exits the unit interval. So I start Brownian motion at some point in the interval, and I track it until it hits. I record that time. That's a random variable. It depends on the Brownian path that I happen to be looking at. Okay? Now, I want to build a number out of that. So to do it, I just compute the average, given a starting point. And what Brownian motion is really a collection of curves and a family of probabilities that allow you to do things like this. Okay? You can build averages. Okay. So then it turns out it's a fundamental, in some sense, this is the reason that stochastic calculus was built. It is an immediate corollary of the fundamental theorem of stochastic calculus, that if I compute the average of this exit time, what I get is that function U1. That's where it comes from. Okay? Right. And it boils down, the corollary itself, the proof, boils down to something very simple. You just have to know that U1 satisfies this Poisson problem. Okay. So once I know that U1 satisfies this Poisson problem, I just look up Ito's theorem. I use U1 on the left-hand side of Ito's theorem. This is what I get when I compute an average. Okay. Right. So if this were all true on the unit interval and nowhere else, it would be of limited utility. In fact, you would have just seen pretty much everything I want to say. But it turns out it's not. Right? This is a general fact, a very, very general fact. It has something to do with geometry and with processes. Okay? So, in fact, I'll say a bunch of words. If you don't know what they mean, it doesn't really matter. The point is, this is a general fact. Okay? So if I've got some complete Riemannian manifold, I take any domain in that manifold that I can think of, say, as a disk or a rectangle or something like that, yeah? Then there is such a thing as Brownian motion on that manifold, and there is such a thing as exit time from that domain. And there is an operator on that manifold, the Laplace operator. So the Laplace operator in one dimension, remember, is just two derivatives. So what I'm doing is giving you a dictionary between the problem that I actually looked at and a general fact. So it turns out that if you solve the same problem i.e. the Poisson problem with zero boundary data, you get the same fact. And again, this is true in horrifying generality. It's also true for other diffusive processes. Okay? All right. So this function, let's see, can I go back? Yes. This function U1 has a name. It's called the torsion function or the landscape function. So landscape is kind of new. It's been called the landscape function in the last 5 to 10 years. Before that, it was called the torsion function, right? It has a very long history. It turns out that it was first investigated back in the 19th century by Saint Venant, who was interested in elasticity. And for planar domains, Saint Venant looked at the integral of this thing. So remember, this is the thing I'm looking at. It's called torsional rigidity. And what it is a measure of the torque required if you hold a cylinder of unit height, you hold the base, you twist the top. The amount of torque required, to twist the top relative to the base, a radian, is this T1D. That's something to be very interested to somebody who's interested in building bridges, for example. Right? In the 20th century, there are a ton of other applications involving elasticity, et cetera, et cetera. And recently, there's a lot of new interest in this. The work of Philoche and Meborata, right, appears in the Proceedings of the National Academy in 2012, where they use this to give fine detail for density of states problems. Okay, so it's a big deal. Now, it turns out that in the problem that I gave you, there was a U2 also exists. And it turns out that that U2 depended only on U1, and the same thing is true in horrifying generality. Right, so if I solve, in other words, if I solve inductively this family of Poisson problems, where I just feed in the thing I got at the last stage, what comes out is an expected value of the kth power of the exit time, so the kth moment of the exit time. It ties it to PDE. Okay? And if I write down TKD is just the integral of that thing, it turns out that what I've done is constructed a bunch of geometric invariants, right? All of these things are invariant under the action of the underlying isometry in the space. Okay? So they encode geometry of the underlying domain. All right? And if you just follow what we've done up to this point, what you see is, so if you go back to the example that I did before, it turns out that you can write the even values of the zeta function in terms of these invariants for an interval. Okay, so many, many other things are going to be true. Let's see, I'm going to do it on time. Yikes. I'm going to look at rectangles in the plane. So all of the tools that I had in one dimension are available here. In particular, the spectral package. You have eigenfunctions and you have eigenvalues. So you can do the same thing, right? For example, you can integrate the eigenfunctions, and sufficient diligence will give you this. Again, another good exercise. If you don't want to do it, there are papers available at the end I can kind of reference for you. Okay? And then I get an expression for the torsional rigidity of a rectangle. Now, so here are two expressions, right? The first one is telling you how I write down the second one. The important thing here is that it's not a single sum, right? It's a double sum. But that's a standard problem in complex analysis. How to get rid of a double sum like this is a standard problem in complex analysis, right? It's a Cauchy residue theorem problem. So you can rewrite that double sum as a single sum. So this formula, I think, appears in a paper with one of my students, Joe Comer. So here's the sum that I was talking about that involves Ramanujan, at least part of it. All right, so here's an interesting fact. Rectangles are invariant under swapping height and length. That means I get two different expressions for the same thing, right, if I swap height and length. So I get an identity. So it turns out that this identity has a long and interesting history, right? So the thing on the left is a product of special values of the zeta function, right? Okay, so a little bit about the history, right? Well, it perhaps not surprisingly was first examined by Saint-Venant and was later rediscovered by Ramanujan, right? And you can find his work on this identity in the edited version of his notebooks. So Berendt has done a great job in providing that, right? If you look at book 2, chapter 14, these two entries involve that identity that was up on the board. Okay. And in fact, what Berendt noticed was that you could actually generalize those identities using modular forms and symmetry. So the fact that we saw that there was this identity that comes from this underlying symmetry is a general fact about forms that are invariant under the action of some finite group. Okay, that's what's really happening here. And there are additional identities if you're interested. There's a paper of Xu. This is, I think, it appears in the archive in 2017. Okay. Now, I have a whole collection of moments, and all of them are invariant under the switch of H and L. So I get an infinite family, right, of identities. In particular, I'll get one when D equals 2. So here's a theorem that I'm not going to prove. If you're interested, I can kind of give you the preprint. But it's an expression for the second moment of a rectangle. And what you'll notice is that it has roughly the same form as the expression I gave before. The difference is that now instead of having a single infinite sum, there are two. Okay? But it is still the case. So first thing to notice is that the second moment factors as a function of H and L and H over L. So when I switch those, I get V inverse. So I get something that looks exactly like what I had for T1D as far as finding an identity for infinite sums goes. Right? So that invariance under exchange gives an identity, and I get more identities for every moment. Right? Let's see. I think I've got 2 minutes, but I'm not sure I have anything else to say, which means I probably went too fast. I guess I could say, because I have, whenever I have a spectral package, so the summary here is this. Whenever I have this spectral package, whenever I know the eigenfunctions and eigenvalues for a domain, the Dirichlet eigenfunctions and Dirichlet eigenvalues of a domain, and I know there's a symmetry of the domain, I get formulas like this. All right? And that is a very general and useful fact. This is the first calculation along those lines. Thanks.
Any questions?
As of now, have you only been exploring rectangular domains, or have you also explored the disk-like domains?
So the question is, up to now, have you explored any domains other than rectangles? And the answer is yes. So there are two things that I've done in addition to this. One is to look at disks, for example, and ovals. And there you get expressions involving Bessel functions. Okay, instead of sines and cosines and hyperbolic trig functions, you get Bessel functions. And then also, I've looked at quantum graphs. So quantum graphs look like intervals that are joined together. And at the intersection of those intervals, the join points, there's a special boundary condition, the Kirchhoff condition. You can solve explicitly for these things, and the graphs themselves have symmetries built in. So you get very pretty results. Is that good enough? Okay.
Pleased to introduce Travis Kowalski, award-winning author Travis Kowalski. He and I also go way back, so I'm thrilled to have him here. He'll be talking about the fundamental theorem of stararithmetic.
Thank you, Bill. So I'm going to first apologize. Right now you've been getting brilliant ideas, and your head is probably like mine, just swimming with things that you could investigate and give to students. And we're going to take a little bit of a breather right here, because I looked at this and went, you know what? Squigonometry, that's a portmanteau of squares and trigonometry, and we're going to play with parameterized functions and geometry. I'm going to stick with that part. So we're going to play with parameterized curves, we're going to play with geometry, and I'm going to make a portmanteau, but that's pretty much how much connective tissue we've got, although you'll see ideas rooting around in here. And so this is based off of undergraduate work that I did with two of my students, Tom Lippincott and Sarah Riley. Sarah just graduated this year with her Bachelor's of Science in Mathematics, so hooray for her. Tom got his computer science degree, lost him to the dark side. But this is actually motivated out of work that I was doing in summer projects with Lakota, Nakota, Dakota kids on sacred geometry. So we were playing around with stars. And so what we're going to do here is not that project. That was chalk and us playing outside, which I would have loved to have done for all of us, but didn't quite fit the vibe. But what we're going to do is we're going to talk about arithmetic with stars. So the objects of our talk are going to be star contours, which are essentially star polygons with a global orientation. If you've got those, you can actually make an arithmetic operation on them. There is a binary operation that allows you to combine smaller stars into more complicated stars. And what's amazing is that operation allows for unique factorization. You can decompose stars into simpler stars in a unique way. It turns out that that object has cool properties, but it's not a group. But if we introduce an equivalence relation, we can make it a group which is isomorphic to the additive group of the rational numbers modulo the integers, which means that adding rational numbers has a unique factorization result, which is weird because those aren't usually words that get mushed together. So let's get started. We're going to talk about star contours. So we're all complex familiar right now. I'm just going to point out, I'm going to use two concepts quite a bit in here. We're going to have our plane as the complex numbers. I'm going to use the nth roots of unity as sort of my reference point. So those points are uniformly spaced around the unit circle, with one of them being the point 1. And I'm also going to use the symbol bracket ZW to indicate the line segment that goes from the point Z to the point W, the actual parameterized line segment. So not just that geometric curve or that geometric set of points, but an orientation. So if I've got these two things, a standard star contour is going to be an object, and we take two integers, k and an n. So n is going to be the number of points of the star. K we're going to just kind of call the skip step right now. And the basic idea is you're going to take the line segment that goes from 1, the 0th nth root of unity, and connect it to the kth nth root of unity. So you got that line. Then what you're going to do is you're going to rotate that line by multiples of 1/nth of a full rotation, and you're going to do that n times. So this object right here is just an oriented star polygon. Do any of you guys know anything about the Schurfli number or the Schurfli symbol? Cool, then I don't have to justify the fact that the symbol I'm going to use is the reciprocal of the more established one. So we're going to call this symbol the kn star, bracket k, line n. And so let's get moving with this thing. So just to give you an idea of what we're actually doing here, the picture version, is if I want to do the 3/8 star, I take the line segment that goes from 1 to the 3rd eighth root of unity, that guy, and then I'm going to rotate it by 1/8 of a rotation 8 times. So in the process of doing this 8 times, the result I'm going to get is a complex contour in the plane, closed curve. Its image is a star polygon, and it has this global orientation, in this case, this global positive orientation. On the flip side, the negative 3/8 star, I would start off by taking the line segment that goes from 1 to the negative 3rd eighth root of unity, and then rotate that 45 degrees 8 times. The end result is going to be the exact same image, but the opposite global orientation. I've once given a talk where I asked people to draw stars, like just a 5-pointed star, and the sheer animosity between the people who draw the stars in the clockwise direction and the anti-clockwise direction was surprising as all get out. No one cared where you started. It was the orientation you did it. So let's go on with here. So this bracket symbol, I just a couple of things to point out about it. It's not unique to a star. The Kn star and the Mn star are the same as long as K and N differ by a multiple of N. As complex contours, the negative Kn star is just the opposite of the Kn star. Same shape, opposite orientation. We just saw that. I've been using orientation in sort of an intuitive ones, but I can assign sign to it. These are contours. You can do their winding number. They go around the origin. If you compute the winding number for these, we're going to say that a star is positively oriented if it's got a positive winding number. It's negatively oriented if it's got a negative winding number. And in fact, the winding number over n, that's the star you're looking at. So it's kind of nicely tied to these complex notions. When I draw pictures too, I'm going to have negatively oriented things be red, positively oriented things be blue, right? In the red, that's the bad thing. You'll actually notice I put non-positive and non-negative in my pictures because there are two special case stars. The 0n star, which just consists of the nth roots of unity. It's the only star contour that's disconnected image. Its winding number is 0, so it doesn't have a positive or negative orientation. And if n is even, then the n over 2n star is an asterisk. So it's the only star that actually passes through the origin. That kind of screws up your winding number integral when you have to divide by 0. So it doesn't have a positive or negative orientation either. And then here's what some of these things look like. And so I'm not used to staying in one spot, so I'm going to have to run over here from time to time. But these pictures aren't just pictures, right? This picture, you're supposed to be thinking this way. It's blue. This picture is that way. It's red. There's an orientation. There is a story in here too. So using these numbers, right, we've got a 1 5-star, a negative 2 5-star, a 2 6-star, a negative 2 8-star. There's an asterisk, the 5 10 star. That negative 47 120 star is just pretty. And it will come back a little bit later on. I will point out that the 1 4 star, that would be the p equals 1 squiggle. And the 2 4 star, that's the p tending to negative or p tending to 0 squiggle. So some of our squiggles, our squircles, are running around in here. And then more generally, just a star contour in general is anything who looks like one of these things up to a dilation, rotation, translation. And because I don't want to keep saying star contour, I'm going to cut down 33% of the talk by just using the word star from now on. All right, so before we get to the arithmetic part, I want to talk about a couple of historic facts that have been known about star polygons. Oh, I forgot to turn my timer on. So one of them is the idea of simplicity. So a simple star is just one that you can draw in a single stroke. How I can translate that into this language is saying that the star contour is what you would get by taking that generator, and instead of rotating it by these little 1 over n rotations, you rotate it sufficiently so that the new one starts where the old one ends. So like a 3 8 star, the construction on the left is going to be the star contour construction. The construction on the right is the simple construction. 1, 2, 3, 4, 5, 6, 7, 8. At the end of 8 strokes, you have the same complex contour. That's simple. The 2 8 1 isn't. So the one on the left, rotations by 1/8 each time. One on the right, tip to tail. 2, 3, 4, 5, 6, 7, 8. So at the end of these 8, the objects aren't the same. This is not a simple star. So it's well known that stars are simple if the skip step and the number of points are co-prime to each other, and more generally, if d is their greatest common divisor, the star you're getting actually consists of d copies of a simple star embedded and rotated around. So there's 1, 3, 2, 6, 3, 9, 4, 2. All of those fractions reduce to 1/3, and 1/3 is that triangle that you see embedded in each one of these things. That simple star that's embedded doesn't traditionally have a name, but I'm going to call it the core, and here's a terrible formula for what the core is. But the basic idea is that every star is just a core star and then rotated copies of it to build something more elaborate. Now, the core is actually one of two ideas that sort of have a historic roots in them too. The idea that you can find stars inside of other stars. So if I take the 2 8 star, the core is a subset of that. That's another star, the 1 4 star. But if you took all 8 sides of that 2 8 star and shrunk them down by about 60%, you would have a perfect copy of a 1 8 star rotated inside there. If you were to take the 8 sides of that 2 4 star and extend them to about 3 times their original length, you'd have a perfect copy of a 3 8 star running around inside. Now, this is well known to people who do star polygons. If you take any two 87 pointed stars, there is a smaller copy of one of those stars embedded inside the other one. It doesn't have a name, but the idea of sort of scaling things up or down to build other versions reminded me of linear independence, but I'm talking about scaling sides, so I'm going to call this lateral dependence because I like puns. So, dad jokes right here. I'm all over these things. So, a smaller star is laterally dependent on a larger star if there is some subset of the sides of the larger star who can be extended or shrunk uniformly to form a copy of the little star. So the work that we saw there, the 1/8, the 3/8, and the 1/4 are all laterally dependent on the 2/8. The 2/8 is laterally dependent on the 1/8 and the 3/8 because you can shrink or extend the sides. It is not laterally dependent on that 1/4 because the 1/4 is small. The 2/8 is big. You have to be smaller. So some observations, also the core of any star is going to be laterally dependent on the stars that it builds. This relationship is reflexive, it's transitive, it's not symmetric, and it's independent of orientations. All right, so those are the historic trends right here. I guess maybe the one theorem that I can say about this too that's relatively easy to prove is that an n-pointed star is laterally dependent on a q-pointed star if n divides q. So there is this nice piece of basic arithmetic that connects the geometry of these two things together. Alrighty, so it's just some pictures so you can kind of see what these look like. There is a negative 2360 star. The 416 star, that's 4 interlocking squares. 16 does not divide 60. It is laterally independent from that one. I have no cool pictures to show you for that. But if I take the core of the 416, that would be a square, the 1/4. 4 divides 60, it's laterally dependent on that red one. And there is the little one. There's a tiny copy of the 1/4 hidden inside that star. The 516 star is visually hard to distinguish from the 416 star if you were to look at them. But 15 divides into 60, that means there's a copy of it inside there. That's the idea of lateral dependence. So lateral dependence is you take one big complicated star and you turn it into little tiny simpler stars. They're less complicated stars. Now let's talk about the arithmetic process. So the arithmetic process, can I justify that equation right there? And that's an equation. I'm going to combine two stars to build another one. So how would you take that 3/8 star and that 2/6 star and make a new star? Well, you could smush them together, but that ain't a star. But you could focus on the things that make stars contours, star contours, number of points, and the generator. It would make sense that if you're going to take two little guys and build a big one, you would want the little guys to be dependent on the thing they built. You just would kind of want that. And so then, that's the picture that focuses on those elements. If I want to talk about the number of points, I would want it to be a common multiple of the number of points of the two sides so I could at least talk about dependence between them. In this case, it'd be a multiple of 6 and 8. 24 is the smallest. How would you build a generating arc? Well, the generating arc is telling you how much you're sweeping around the circle. If I'm going to combine two things, why not sweep them out in sequential order? Do the first arc and then do the blue arc after that part to make this arc, which in this case would be 3/8 plus 2/6 of a full rotation. I got 17 points. If you count, I've actually gone 7 points down. This is the negative 7 24 star, which looks like that. So the general process, you take two stars. The number of points is the least common multiple of the points of the two stars. And then the skip number is the combined arc multiplied by the number of points so that you end up someplace on the circle. If you do a little bit of geometry, what this really means is that combining stars is functionally equivalent to adding the fractions, but making sure you write it in one particular form. It has to have the right denominator. So let's just do a couple of arithmetic problems. The 2/7 star and the 1/6 star get you a 1942nd star. So if you would like, heptagram plus hexagon equals Ruth Bader Ginsburg descent necklace. Heptagram plus negatively oriented hexagon equals ring. I'm bringing this one up just to point out that the orientation matters, right? Those are both hexagons, but one is positively oriented, one is negatively oriented, and that has all the effect in the world of the final shapes. Just another variation of this. I'm not going to put grams on these ones, but I have a 3/8 star and a 5/12 star and a 3/8 star and a negative 5/12 star, just to show you again, orientation matters, and also the orientation of the final product isn't determined by the orientations on the stars who are used to build it. Maybe this one's a less interesting one, but more interesting on the algebra side. If you take a triangle plus hexagon, you get asterisk, but also Star of David plus hexagon equals the same asterisk. So we're going to talk about some of the arithmetic properties of this. This operation is commutative, it's associative. The one-pointed star is an identity, it has a negation operation. But because stars always get more points, no one ever gets back to 0, 1. No inverses, not a group. Also, because I had that one equation before, ST equals RT doesn't necessarily mean that the left-hand sides match. It's not a semigroup. It doesn't have cool algebra properties. If you look at only the n-pointed stars, you get Zn in surprising or in disguised form, but we know Zn. What this thing has is it has a factoring property. So the usual definition, if I want to factor something, I need kind of words for that. So we're going to say a star is reducible if you can break it apart as a combination of two stars who have smaller points, both of them having smaller points. Obviously, if you've got a prime number of points, you're not reducible, because the least common multiple of any two things who is a prime, one of them is that prime, and that's going to be true for prime powers. The converse is also true. If the number of stars factors into two distinct primes, you can actually factor it. In fact, if you can take the number of points and write it as a product of two co-prime numbers, then you can factor it uniquely. The basic proof goes something like this. Here's the equation that I'd have to satisfy if I wanted to take a big star and factor it into two small things, which would boil down to finding integer equations x and y to xn plus ym equals k mod mn. It's a Diophantine modular equation. Bezos' theorem says that because m and m are coprime, there's always a solution. Diophantus steps in and says, well, there's lots, but they're always unique modulo m or n, and that's the one thing that my star symbol doesn't care about. So the stars are unique. So let's just run this through a quick example. The 73-120 star. I want to factor this. So I got to think, all right, I need coprime factors of 120. So say 3 and 40 as a starting point. I'd have to solve the equation a times 40 plus b times 3 is 73. 40 plus 33 will work. So 140 and 11 threes. And I get this factoring. It factors in the 1/3 and the 1140 star uniquely. The 1/3 star is irreducible. The 1140 star is not, because I can split that up into an 8 and a 5. I repeat the process, and I've got a star who can be reduced into irreducible stars. And this process could be repeated on anybody. Objects who can be factored into irreducible objects. That sounds like a fundamental theorem of arithmetic if I can get one extra thing out of it. What's the one thing that the fundamental theorem of arithmetic also says? Uniqueness. Is this unique? Nope. Ta-da! This is not a unique operation. There are at least five different factorings of this star into irreducible substars. But in 4 of these factorizations, there are dependence relations among the reducible stars. In all these pictures here, in each one of those rows, the yellow star on the right is laterally dependent on the yellow stars on the left, are laterally dependent to the yellow stars on its right. Only one of them doesn't have any of those, and that's the theorem. Every star can be represented as a unique up to order combination of mutually laterally independent, irreducible stars. And this one unique ordering is the shortest of all possible factorizations into irreducible stars. Basic proof is take your number of stars, write as a power of primes, do the factor lemma over and over and over and over again, and then there's a whole bunch of details you got to follow. I'm not going to. But I still don't have a group yet. This is still just a weird collection of things. And so to get a group out of this, there's this calculation. And this is a terrible looking thing up here, and all I want to point out is what it says is this. And I have to yell again. All of these stars have the same core. All of these stars have the same core. This object right here has the same core as the combination of the cores of the other ones. This operation does not preserve simple stars, but it does preserve the cores of stars. So we're going to make an equivalence relation. We're going to say that two stars are equivalent if they've got the same core. And we're going to call this rational equivalence because what it boils down to is that two stars are rationally equivalent if they're the same rational number when you take the brackets off. So that thing down there is what the 1/3 rational star looks like, what the equivalence class looks like for that one element. With this observation, negation and combination are now well-defined operations. It's associative, commutative, and has an identity because we stole that from the previous ones. But now it has inverses. It's a group, an abelian group. And in fact, if you were to erase the parentheses, that mapping is an isomorphism onto Q up to units, up to integers. So this group is isomorphic to Q mod Z. But I did all this equivalence relation stuff. The thing I cared about was the unique factorization. Do I get this theorem? Well, only if I can figure out what I mean by reducible and lateral dependence. So reducible was the idea that you could split the star into smaller things. Now, these are now equivalence classes. They got a bunch of stars with lots of points. Most of them could split. So what would I mean by an equivalence class being reducible? The obvious answer, or an easy answer, would be I want every single one of the elements in there to be reducible. which would mean I really just want the core, the building block one, to be splittable. So that's going to be our definition. And the same thing for lateral dependence. Two equivalence classes are going to be laterally dependent if their cores have the same property. And with these two facts here, this is a theorem. There is the proof. I don't care about that. I got maybe, what, a minute? Oh, I got 2? Oh, well, okay. I will at least maybe say a word or two about this thing. The key part here is that you take that factor lemma, the one that says that if you could split the number of points into 2 coprime elements, that there is a unique factorization, and you beef it up a little bit. You prove that in addition to that, that factoring it involves simple stars if and only if the end result is simple. So with that lemma, you could go through, you take a star, you find its core, you stick it back in the set of stars, you factor it out. It will have simple components, so when you take the equivalence classes, that will be irreducible, laterally dependent. You've got one factorization. Then you grab anything else, switch it back over into S. The objects in there will be simple because they're built out of cores. You go back to this simple factoring lemma. It says, oh, I didn't get a simple, or I didn't get a compound star at the very, very end. It has to be the same as the other one back in S. Details are left to you. I know you've had, 18 minutes to digest this? Get going. What I do want to close with is just this. These are neat kinds of ideas here, and what I want to do is, I don't know a lot more. This is something that we've been playing around with. Getting a hold of this group was Sarah Riley's innovation. I kept trying to add stuff to make the thing bigger. She had the brilliant idea of carving the thing down a little bit. But I want to show you just two interesting connections to algebra, just to kind of show you that this is a geometric way of kind of understanding arithmetic properties. So one of them is this. Any finite cyclic group is isomorphic to a direct sum of cyclic groups, each of prime-powered order, right? This is a special case of the fundamental theorem of finitely generated abelian groups. It's trivial when you talk stars. So you take your finite cyclic group, which is Z mod n, up to isomorphism. You take n and you factor it out into a product of primes, and you grab that group right here, this cyclic group. You take any n tuple here, and you make them the numerators in stars. That star is well defined. The fundamental theorem of arithmetic says the inverse operation is well defined. So that means this direct sum is isomorphic to the set of n-pointed stars. That's just Zn. There you go. There's a nice explicit characterization. Second one is every rational number can be uniquely expressed up to order as an integer plus reduced positive proper fractions whose denominators are powers of primes. So positive, not less than 0. Proper just means less than 1. And so, for example, if I take 11/45, that's -1 plus 4/5 plus 4/9. That fraction that we were looking at before, the big red star, is -1 plus 1/3 plus 2/5 plus 7/8. If you put their negatives on, you get a different collection of fractions. But this is the one and only one way to do this. The proof is essentially any factorization in S, in the equivalent space, boils down to an arithmetic equation which is unique modulo the integer. So I'm going to just end with 2 quick observations here. One is, I haven't talked about the fact that these were complex contours, so you can put integers in front of them. Right? You can make a module out of contours. I don't know if that translates to something interesting on these things. The other tidbit is that if you do geometric inversion, so that's a process that turns lines into circles and circles into lines, every star inverts into these beautiful rose geometric objects who have all of the same lateral dependence properties but in the opposite order. I have been trying forever to figure out if there's a way of making this geometric inverse for stars into some kind of arithmetic inverse, like a left or a right inverse, to make it function something more like matrix multiplication. Got a couple of near misses on that one, but I don't quite know what it is. And if you ask me if there's algebraic utility lists, I'm going to say, I'm a pure mathematician. I like pretty. I was an art major before I was a mathematician, so I go, look at how pretty the pictures are, and that's good enough for me. So if you got hardcore algebra questions, I'm going to just whimper up here, and I might wet myself. Other than that, thank you for listening to me.
So good afternoon, everybody. Welcome to my talk about a tale of two catenaries. So I might be a minority here in the sense that I'm not a mathematician by training. So I happen to be a physicist, although that makes me not too awfully far from mathematics. So I sometimes prefer to call myself an armchair mathematician. So play around with areas that belong to the overlap between mechanics and calculus or calculus of variations and so forth. So this will be the outline of the talk. So we will go through an introduction to the iconic catenary shape and its relation to hanging chains. Then we will briefly talk about stable and unstable equilibrium, the mechanics of that and the math that goes with it briefly. And then we will state the double catenary problem, which is the essence of the talk. And then we will go through the brief analysis and try to get to the answer. And then we will end with an acknowledgement and also a proclamation. All right. So what is a catenary? So the catenary is probably a very familiar shape to mathematicians and physicists. So in mechanics, it's the shape of an ideal, uniform, inextensible string, equivalently a chain or a rope, hanging in equilibrium solely under the action of its own tension and Earth's gravity. Now, the word catenary, interestingly, is derived from the Latin word catena, meaning chain. Interestingly, the English word concatenate also is derived from the same Latin word. So the Cartesian equation is this equation on the right-hand side. Let me get used to this laser pointer here. So this, oops, no, I'm a technophobe, okay. All right, so that is the Cartesian equation on the right-hand side, a familiar equation. So it's basically the plot of the cosine hyperbolic function in Cartesian coordinates. So one important feature, geometric feature about the catenary shape is the realization that all catenaries are of the same shape effectively, but they can vary in size. So here in the Cartesian equation, the parameters b and c, they are related to the horizontal and the vertical positions of the catenary plot effectively, but the parameter a is very important. So that is what effectively sets the size of the catenary shape. So geometrically, the parameter a is the radius of curvature of the catenary at the vertex. So that is the geometric significance of the parameter a. So the greater the value of the a, the bigger the catenary shape is. So these are some playful examples of snapshots of catenaries. So I tried to scale them to the same size so that the fact that all catenaries are alike in shape is more obvious. So garlands, ropes, beads, all forming catenaries when they are hanging in equilibrium like that. All right, so related factoid, ideal arches happen to be inverted catenaries, including the gateway arch, the iconic gateway arch of St. Louis. Although that arch is not a catenary proper, it's actually shrunk in only one direction, which is related to the fact that the linear mass density is not the same. So I just wanted to briefly mention that on the side because some people might catch on that. But it's still a variation on the catenary. And on the right-hand side, we see an artist's rendition of the gateway arch casting a garland on the great Mississippi River. All right, so now about the mechanics of stable and unstable equilibrium in a nutshell. So to make a long story short, in mechanics, equilibrium is a state for a mechanical system or object where every part of that system or object stays at rest without external perturbations. So on the left-hand side, we see a schematic of a marble, something like a marble placed at the bottom of a rounded bowl, so a hemispherical bowl. And that's an example of a stable equilibrium, which might be next to obvious. So if we displace the marble a little bit in any direction from the equilibrium position and release it from rest, it has a tendency to come back to the equilibrium position, obviously, which makes the equilibrium stable. On the right-hand side, we see a marble placed at the top of an inverted hemispherical bowl, which looks precarious intuitively already because it's an unstable equilibrium. Theoretically, it can stay there, but the moment you displace it by any amount in any direction and release it from rest, it will obviously have a tendency to move farther away from the equilibrium position. So that equilibrium is unstable. So what does it mean in terms of mechanics? So the mechanical principle, the concise form of the mechanical principle, which is relevant to our work, which we will use in our work, is this. So a mechanical system governed by Earth's gravity and ideal, in other words, non-dissipative constraints, happens to be at stable equilibrium when the gravitational potential energy is at a local minimum, and it is at an unstable equilibrium if the gravitational potential energy is at a local maximum. So for a composite object or physical system, by composite we mean something that's comprised of more than one particle, which is placed close to the surface of Earth, the gravitational potential energy can be expressed in this simple form: the total mass of the system times the acceleration due to gravity times the height of the center of mass. Okay. So on the left-hand side, again, we show a schematic of a hemispherical bowl. Now the bowl itself is just standing at rest on its vertex, and that happens to be a stable equilibrium as well, which might be somewhat obvious to us from experience or intuition. So what we show is that when we tilt the bowl, that hemispherical bowl, in any direction, the center of mass, this point right here, that tends to go up whenever you tilt that in any direction with respect to the equilibrium position. So because the center of mass is going up in terms of its vertical height, the gravitational potential energy is going up. So that means that at this equilibrium position, it's at stable equilibrium. Oops, no, wrong. I'm really messy with this. Okay. So yeah. So it means that at this position, the center of mass, the vertical height of the center of mass is at its local minimum, which makes the gravitational potential energy a local minimum as well, making the equilibrium stable. On the right-hand side, we have a football standing on its more pointed vertex, and it looks precarious, almost impossible, because it's an unstable equilibrium. And this schematic here shows that whenever it's tilted in any direction, the height of the center of mass goes down, which makes the vertical height at a local maximum at this configuration, making the gravitational potential energy a local maximum as well, which makes that equilibrium unstable. All right, so now let's give us a sweet example of a transition from stable to unstable equilibrium. So let's consider the equilibrium of a uniform hemispheroid standing on its vertex. So we start with a hemisphere, and then we consider progressively more oblong hemispheroids standing on its vertex. And already we talked about how the hemisphere is at stable equilibrium. But from intuition, you can already tell that as we consider higher and higher aspect ratios, and in this context, the aspect ratio is defined by the height at the erect position divided by the equatorial radius, so that makes the aspect ratio 1 for the hemisphere. So as we consider higher and higher aspect ratios, there must be some point where the equilibrium transitions from stable to unstable. And these are the plots of the actual plots of the potential energy as a function of tilt angle. So the tilt angle of 0 pertains to that erect position that we showed in this slide. And we see that for a hemisphere, mu equals 1, it's at a stable equilibrium, which makes the derivative of the potential energy with respect to the position coordinate, which is theta here, 0, and the double derivative positive, which is again a known tool for determining the local minimum, which students learn in high school or college already, so should be quite familiar. And actually, the double derivative is positive for this whole range of theta incidentally as well, which is also evident from the fact that this plot is concave when viewed from the top. The double derivative is positive for that whole curve, including the equilibrium point. Now, for the critical value of mu equals 1.26-ish, I get this sweet transition where the double derivative as well has become 0 at the equilibrium point, which makes this a flat minimum. So you have to go all the way to the fourth derivative, which will turn out to be positive, to determine there's still a stable equilibrium, but a flat or critical stable, no matter depending on what you choose to call it. So now when we get to an even higher aspect ratio, really oblong hemispheroid, now we see that the erect position has become an unstable equilibrium, where the double derivative has become negative, which is also manifested by the fact that around the point, the plot is convex as viewed from top. Also interestingly, now that that equilibrium in the middle has become unstable, two new stable equilibria have emerged symmetrically on the two sides of the midpoint. Okay, now let's get to the double catenary problem. So this is the story behind it, the nascence. So during a winter break trip home, a few winter breaks ago, when I was just playfully handling my mother's beads, I noticed something interesting. That is, with this particular loop of beads, when I was making double catenary shapes like this with my fingers, even when I started from the two hanging segments being identical, when my fingers were far away, when I drew my hands together and the catenaries, both catenaries started becoming narrower, I saw that the two segments had a tendency to move away from each other, which got me intrigued. And to make a long story short, I posed a mechanics problem like this. So take two frictionless pins, which are just frictionless geometric constraints, which are at the same vertical height, and the distance between them is d, which we will set to 1, the numerical value of 1, without losing generality. And let's take a single closed loop of an ideal, uniform, inextensible chain, but it's a closed loop of this, which of course must have a length that's greater than 2, to be able to be draped over these two pins and make a double catenary shape like this. And it's not too hard to prove that the configuration of these two segments being identical is actually an equilibrium configuration. The question that's more subtle is that if that equilibrium will be stable or unstable. All right, so to get to the answer, we first consider the variation of the potential energy of a single hanging catenary segment, which is hanging from the two pins, a single segment. And we study the variation of the potential energy as a function of length. So these are familiar expressions for length, which was more familiar to all mathematicians, the expression of the length in terms of the Cartesian coordinates. This is potential energy, which should be familiar to physics students and maybe many math students as well. So the gravity, vertical height y, and dm is the mass of the infinitesimal element. At this point, from this point onwards, we take the value of g, the numerical value of g, and the linear mass density both to be 1 without losing generality, very important. And we get to these expressions for the length and the potential energy. Once again, the reference level we took for the potential energy, the 0 level, is the vertical level of the two pins, the most convenient. And we are considering the potential energy of this hanging single catenary, the potential energy of that as a function of length. It turns out that the potential energy does not have an explicit functional form in terms of length. But both the potential energy and the length can be expressed in terms of explicit functions of the parameter A independently. So using A as a parameter, we should be able to plot the potential energy against L to study how the variation of that would be. And we see this interesting trend. As expected, so let's just go back to the previous slide for a moment. So as we consider, for the value of d being fixed at 1, as we consider greater and greater lengths with the same linear mass density of the hanging segment, we expect the potential energy to go down because I have more mass and the center of mass is also going down. So the potential energy must be a strictly decreasing function of length. And that's what we get when we plot it, but we see something interesting. It starts as a concave function, and then at some point it becomes convex. So the left side is for small values of L, the right side is for large values of L. That indicates that there must be an inflection point somewhere when it transitions from concave to convex. So it turns out that the potential energy, the double derivative of the potential energy with respect to length can be expressed in this form as a function of A once again. And if we want to find the inflection point, we have to set the whole thing to 0. And that means setting this numerator to 0, which gives us a transcendental equation, which we can solve numerically to obtain the corresponding critical value of A, from which in turn we can find the critical value of L, which is about 1.257-ish. So at that value of L, the double derivative becomes 0. What does it mean, though, for our double catenary? Now, for the double catenary, again, remember, at every realization of the experiment, we are taking thought experiment, of course. We are taking a fixed length of a loop. And then we are considering different configurations. So this system effectively has 1 degree of freedom. So the total length is fixed, and if we call L1 and L2 the lengths of the two different segments, then the sum of L1 and L2, no matter what configuration we consider, must be the fixed L, which makes the differentials add up to 0. So because this system obviously has 1 degree of freedom, we can choose either L1 or L2 to be our independent variable. So we choose L1 to be the independent variable. Really, the two are equivalent. So let's take L1 to be the independent variable. And then the net potential energy of the whole loop that we need to consider to study stability at the end of the day is the simple sum of the potential energies coming from the two different segments. So when we do the math, we take the derivative of the net potential energy with respect to the independent variable. It turns out to be effectively the difference of the derivatives of the potential energy with respect to length coming from the two different segments. And for the double derivative, it turns out that the individual double derivatives add up. So in other words, the double derivative of the net potential energy with respect to L1 turns out to be the sum of the double derivatives coming from the two independently hanging segments. So what does it mean for the midpoint, the configuration of the two segments being identical and both being equal to L over 2, capital L over 2, half the length of the whole loop? So for that configuration, the derivative of the net potential energy with respect to the independent variable becomes 0 because these two derivatives have the same value. And for the double derivative, we see that the double derivative at that configuration becomes exactly twice the derivative of the potential energy of a single hanging segment with respect to its own length. But we saw that this quantity has a transition point. That becomes 0 at some point. So if we, to make a long story short, longer story shorter, combine all the logical components together, at the end of the day, we can infer that for the length of the whole loop, there exists a critical value given by twice the critical value of the individual segment we obtained before. So the critical value of capital L, the whole loop, is about 2.51-ish. So there exists that critical value for capital L, for which when the length of the loop is subcritical, below this critical value, the configuration of two identical segments stays a stable equilibrium. At the critical point, that configuration becomes a critical equilibrium. And for supercritical values, so when L is greater than that critical value of 2.55-ish, now the midpoint, the configuration of two identical catenaries, becomes an unstable equilibrium. So that raises the question, if that is now that midpoint is becoming unstable, by midpoint I mean L1 equals L2 equals capital L over 2. If that is becoming unstable, then what is the equilibrium, the stable equilibrium configuration? You can show, and of course I'm omitting the proof here. I believe I have proofs for all these little findings. So you can show that for supercritical values of capital L, exactly two degenerate new stable equilibrium configurations emerge symmetrically about the midpoint. Here is a little plot against the independent, the chosen independent variable of L1, the net potential energy. subcritical value 2.2. This midpoint equilibrium is stable as expected. This is the critical equilibrium, and here the equilibrium has become unstable for the supercritical value, and I have two new stable equilibria on the two sides symmetrically. Qualitatively, these graphs are exactly similar to what we had for the transition from the hemisphere to the prolate hemispheroid. So that consideration that we showed before. So this is a little bifurcation diagram, awfully reminiscent of phase diagrams in physics. So the bold lines were showing the configurations of stable equilibrium, and the broken line here is the configuration of unstable equilibrium past the critical point. So conclusions for the double catenary system at the end of the day, we have a critical value of the length of the given loop to be about 2.5154-ish, for which when I have a subcritical range, when I'm in the subcritical range, the configuration of two identical catenary segments is a stable equilibrium. At the critical point, that configuration is critically stable, and for the supercritical range, when the length is greater than the critical length, the configuration of two identical segments has now become unstable, but now two new degenerate stable equilibria have emerged symmetrically about that midpoint. So acknowledgements, my parents, especially my mother, for letting me play with her beads. That gave me the first idea. The anonymous reviewer of Mathematics magazine, I don't know if he or she is here today, but I'm thankful for all the great suggestions. This work was eventually published in Mathematics magazine. And Dr. Anton Konichev, my dear friend and fellow physics professor at IUS. And last but not least, I want to mention this. So much of my formative years were spent in India, where garlands are ubiquitous. So the encounter with a catenary in the form of a garland would happen all the time, and I was always attracted to the beauty of garlands and also the graceful shape of the catenary. So I considered this work my humble ode to the graceful, auspicious shape of a hanging garland. Thank you. Yes.
I have a couple of questions.
Of course.
One is actually a very general question about catenaries that I had for a long time.
Okay.
Maybe you are the expert. I should
Oh,
ask you.
well, I doubt, but I'll try.
So what if you look at the hanging chain problem
Yeah.
when the gravitational field is not uniform? Do you get a different class of curves?
I believe so.
Okay, have those been studied?
I vaguely remember to some extent, but I don't know all the details. But yeah, it's a very long chain where like it's so long that the acceleration due to gravity is effectively dependent on altitude, then of course you have new interesting shapes. Yeah.
And the second question I have is that, this number that you got,
Yeah.
2.5,
Yes.
you approximated,
Yeah.
numerically 2.5 something, right?
Yeah, yeah.
So it would be very interesting to study the exact number and see if it has any bearing on the structure constant, maybe the acceleration, the universal constant of g, or something like that, or pi. It would be nice to see theoretically what that would be.
Okay.
You understand my point?
So if that constant is in any way related to the, say, acceleration due to gravity or any physical constant, okay.
Or mathematical constants.
Okay, well, for a mathematical constant, I have something to share, so I'll be brief. For physical constants, I'm not too sure, but I may be wrong. But for mathematical constants, and this is something that might be known to some of you in the audience, this constant also shows up. The individual length, 1.2, so it's a half of the critical length at the end of the story. So that first critical length that I calculated shows up in a different context, and also the corresponding value of A, the parameter A. So the iconic surface area minimization problem, the equivalent of the soap bubble problem. So for a general situation, to make a long story short, I'm making a very long story very short here, and also like sharing whatever little I know. If you have a catenary solution at all by solving the Euler-Lagrange differential equation, then in general you have two catenaries. One is called the upper catenary and the other is called the lower catenary, deep catenary, shallow catenary, whatever. And only the upper catenary gives you the actual local minimum, and the other solution becomes spurious. And when the 2 points are at the same distance from the axis for that iconic problem, you get the same constants. But my problem is a slightly different problem. It turns out that you can map the two in some way, but the mapping is not too obvious, at least to me. So just wanted to mention this, that this constant shows up in a different, more iconic catenary problem as well, which in essence is still a different problem. Yeah. Okay. Thank you for the question. Yes?
So the soap bubble problem you're talking about,
Yeah.
if you take two circles
Yeah.
that are the same radius,
Yeah.
make them out of wire,
Yeah.
drop them into soapy water,
Yeah, yeah,
and you keep them close together,
yeah,
and you pull it out of the water,
yeah.
you'll get a rotated catenary.
Yeah. That's exactly what I was talking about. Yeah.
And then as you move those circles apart,
Yeah.
that catenoid starts to get skinny. That's your A value dropping, right?
Yes, I think if you like pull them apart, then the A value will rise. It will become a broader catenary.
The bubble is going to pop at some point.
Yeah, because yeah.
Your first value, is that like your
Yes, exactly. That is the point I was talking about. Beyond that, a catenary solution is not possible, and it's a Goldstone solution, I think, like, yeah, exactly. But at that critical point where it will pop, when the two catenary solutions merge and you get a single catenary, that is the point for which the constants match my constants here in this problem. Yes. Yes, please.
Have you ever thought of making a physical model and as a demo to watch the link?
I'm a very bad experimentalist. So, but that will be a nice student project, whoever, yeah. But that's definitely a good prospective project. So I would invite more questions, but anybody, any more questions? Otherwise, I would like to say a little something with Bill's kind permission. So this gift is really sentimental for me because I'm hardly knowledgeable on squigonometry, so this was a delightful introduction today. But the generalized circles, which are related to this beautiful gift, strikes a nostalgic note, because at some point I worked on the mechanics of sliding ladders. So that's an iconic problem in calculus, the related rates, but I worked on the actual mechanics to some extent at some point, so a physics project, a mechanics project close to heart. And it turns out that when I have a straight line, the model of a ladder sliding between two perpendicular wall and floor, the midpoint of the ladder follows a circle. But what's more interesting is that the envelope of the ladder is an asteroid, which is like less obvious. So thank you so much, Bill, for this wonderful gift.